identified and so indicated the information I provided yesterday to our Canvas website. All right, let's finish chapter 16 on solutions. First, a couple more comments on osmotic phenomena, which we really have already mentioned. .876% by mass sodium chloride solution is osmotically equivalent, has the same colligative properties as human blood serum. So, people who operate in clinical chemistry laboratories a long while back discovered that a simple way to preserve a sample of human blood cells is to immerse such in 0.876 mass percent sodium chloride solution. Physiological saline, so to speak, because of its ability to preserve human blood cells, because again of equivalence and colligative properties as human blood serum. What would happen? This is my $64 Van Gogh sketch of a human blood cell. I don't know if your blood cells look like this, nor do I want to know. Okay. If a blood cell is immersed in pure water, then the osmotic pressure of human blood serum in the blood cell is greater than that from water, the upshot of which is water molecules will flow into the blood cell in an attempt to dilute blood serum and make it colligatively equivalent to that of water. In other words, try to make it like pure water itself. Well, the more water that enters, the larger the cell walls become, eventually expand to the point of rupture. Cells destroyed by explosion. On the other hand, if blood cell sample is immersed, say for example, in sodium chloride solution, which is more concentrated than physiological saline, like 2% sodium chloride solution, now the osmotic pressure of human blood serum exceeds that for the sodium chloride solution, and there would be a net flow of water molecules from blood serum through the walls of the cell, which function as the osmotic membrane of the water molecule flow, eventually causing the blood cell to shrink and destroy by shrinkage, called crenation. This again we mentioned before. Now the last consideration for solutions is that of Henry's law. Qualitatively, Henry's law says, if for a liquid solvent we increase the pressure of a particular gas above that solvent, we'll make the gas more soluble. Nothing fancy about this. Now it is interesting and worthy of note that in general, gases become more soluble or less soluble in liquid solution if the solution is heated. What do you say? Less soluble or more soluble? Less soluble. What do you think? If in beer, for example, ice cold beer versus room temperature beer, or soda pop, because these are both examples of solutions in which CO2 is a gas dissolved in water. Okay, and the warmer solution would be a beer soda pop. CO2 molecules are going to leave much more rapidly and cause the beer or soda pop to become flat quicker. But interestingly enough, there are a few gases which show an increase in solubility in liquid solvents on warming. So we can't make any generalization regarding gas solubility that is applicable on an across-the-board basis as we can with Henry's law. Where again, gas over a liquid solvent, you apply pressure to increase the partial pressure of the gas over the liquid solvent, and you will increase its solubility. This is shown by Henry's law, where concentration as a function of molarity is equal to the Henry's constant. So again, we got one of these K's in here. Not to be confused with other K's like freezing point depression constant, boiling point elevation constant. And then in chapter 17 on kinetics, we'll talk about rate constants, which are also symbolized in small k. Times the partial pressure of the gas. Comment, Henry's constant for each and every gas must be determined by experiment. And I'm pretty sure it must also be determined by experiment as a function of temperature. I haven't researched the issue far enough to know for sure. In any case, the first issue I wish to raise from a quantitative standpoint is to consider the units on the Henry's constant. Well, they follow immediately from this equation definition, this arithmetic definition of Henry's law, where C, which is molarity, is equal to Henry's constant times the partial pressure of the gas. So if we rearrange this so as to set it equal to Henry's constant, which is then molarity divided by pressure. So pressure is in atmospheres, and molarity, of course, is moles of solute per liter of solution. So we see the units on Henry's constant, moles liter atmosphere, per liter atmosphere. Then, there is an illustrative question regarding Henry's law on the middle of page 1623. Since it is exemplified in detail on that page, I see no particular reason to repeat all that stuff. But from the information given in the statement of this question, and answering such, which is on page 1623. The first part of the computation in answering the question is to calculate the Henry's constant for CO2 over water at the existing conditions. This means, for the data given, which if my memory is right, it's 20 degrees centigrade, correct? Okay. At a partial pressure of CO2 of 1 atmosphere over water, liquid, at 20 centigrade, you get a K value of 0.0391 moles CO2 per liter atmosphere. So with an atmosphere of CO2, nothing else, just CO2 gas over water, at a pressure of 1 atmosphere, not a whole lot of CO2 dissolves. We're not surprised at this because we know CO2 is not polar and so is not going to show particular solubility of consequence in water, even at this high partial pressure. The question then goes on to say, if I have a sample of air over water, like for example the air which is in this room at 20 degrees centigrade, which is only 0.0360% CO2, which means the partial pressure of CO2 gas in this sample of air is only this small fraction of an atmosphere. How much CO2 is dissolved in the water with air above the CO2? I mean, with air above the water, based on this Henry's constant we've just developed. Well, the arithmetic is there molarity of 1.4 times 10 to the minus 5, which again keeps with CO2 not being particularly soluble in water. But of course, the air sample above the water in this case is not very rich in CO2 at all, like the air in this room. Although, there, now I'll put some more CO2 in here. Now, a couple of questions which follow. 1628 says, based on Henry's law consideration, well, I don't know that it goes on to say that, but it implies that. With Henry's constant for neon and Henry constant for argon each being supplied, what will be the freezing point of the resulting solution? Now, in the main, what I wish you to realize about this question as it is stated is that it requires that you make two considerations and put them together. Henry's law, so that we can figure out for this neon-argon mixture how much of these gases are dissolved in water. And then freezing point depression as a consequence of solute particles being in water, making it a solution. So two parts. Henry's law, you get at the solubility of each of these gases in water, and then freezing point, or we could have instead calculated the boiling point. Well, the David Gibbons tell you, and I think I got this one wrong. This is supposed to be neon gas here. This is neon gas. This is argon gas. There's the Henry's constant for neon gas, again determined by an experiment. 0.00055 moles per liter atmosphere, versus argon, which has this Henry's constant of 0.0026 moles per liter atmosphere. So even though neither of these Henry's constants are particularly big, we find them to be larger than Henry's constant for CO2. Oh, pardon me, smaller than the Henry's constant for CO2. And we see at a glance that the Henry's constant for argon is considerably bigger than the Henry's constant for neon. Again, even though neither are big at all. Why might you expect, this is question 29, why is it reasonable to expect, even without knowing the values for these Henry's constants, that the Henry's constant value for argon will be larger than the Henry's constant value for neon? Is that reasonable? What is that? What does that mean? Bigger. And so? To what intermolecular attraction force does atomic mass or molecular mass relate? London. Greater London force of attraction. Okay. And of course, if we have a gas which is rather soluble in water because it's polar like water, or even far more soluble in water because it's hydrogen bonding, then you're going to have a lot bigger Henry's constant. Okay? In any case, this shows how to get the net molarity for the solution with the two solutes being neon gas and argon gas respectively. And then to calculate, as instructed, the freezing point temperature for the resulting solution, we just apply the freezing point depression expression. For this case, this K is not a Henry's constant. This is the freezing point depression constant for water liquid, which is minus 1.86 degrees centigrade per molal. Well, molal, this is really M. This is a particularly dilute solution with water being the solvent. Molar and molarity, molar concentrations and molal concentrations are practically speaking the same. Remember why? Well, what's the definition of molarity? Moles of solute per liter volume of the solution containing that solute. Well, if the if the solvent is water, because in molality, it's per kilogram of solvent, isn't it? Well, for a dilute solution, if the solvent is water, then it's practically speaking a solution system which is mainly water by far. Well, then it's like a liter of water. What's the mass of a liter of water? Kilogram. Done. So you do your obvious arithmetic, you get minus 0.0018 degrees centigrade, and I'm telling you what, you better have some good temperature reading gadgetry. Find this freezing point temperature for water, for this water solution, which is only this much less than 0 centigrade. All right? And on we go to chapter 17, kinetics. A wonderful chapter. But a chapter on a topic with which we cannot deal extensively in first-year chemistry or first-year chemistry laboratory. Most true kinetic investigations will involve some pretty sophisticated kinetic considerations. Depend on sophisticated chemistry, which is yet, for the most part, we haven't been able to get at. And oftentimes, some rather detailed, high-powered mathematics, which we're not yet able to get at. Now, Professor Smith over here would like us to do that, but I'm not going to accommodate him. Plus, in our laboratories for first-year chemistry, we're hardly going to go in there with millions of dollars of equipment so we can do legitimate kinetic experiments on all sorts of reactions. The gadgetry to do kinetic investigations is oftentimes quite sophisticated, delicate, and expensive. And we're not going to put people in there without any particular degree of laboratory experience in a laboratory that's outfitted with all this fancy stuff. But at the minimum, we'd have to spend a lot of time to teach you how to use it. And wouldn't have any time for anything else. Unless, of course, you were of a mind to take a 1-hour credit laboratory course for general chemistry and spend 40 hours a week in life to do this. I'd be happy with this. I don't know how many students would be happy. Well, we'll limit it to 30 hours a week. How's that? But, as we have mentioned before, in the main, chemists have 2 ways to follow the progress of a reaction. And chemists are spending, as I see it, more time running and studying reactions than any other single activity in which chemists engage. Well, how do I study reactions? I study them thermodynamically or kinetically. Now, in the main, what's the difference? From a thermodynamic standpoint, which is most of what we do in undergraduate chemistry classes, we pay attention to the energy, structure of the original reactants and compare such to the energy structure of the final product. Makes no difference from a thermodynamic standpoint what takes place during a reaction as reactants interact with each other to become products. Don't pay attention to that. Don't worry about time. Thermodynamics, practically speaking, is a study of chemistry without any dependence on time. You don't care about time. But when time is involved, now we're going to study the reaction kinetically. How fast does the reaction go? And if you're dealing with a reaction which is particularly fast, for example, bronze telluric acid-base reactions in water solution, have been recognized to transfer H+, because that's the heart and soul of any Bronsted-Lowry acid-base reaction, on the order of nanoseconds. You better have some pretty good gadgetry to be able to measure this kind of stuff. That's fast! That makes a blink of an eye look like something that's really slow. Really slow. Well, that has to do with reaction rate. In other words, practically speaking, there's two parts to a kinetic study. We're looking at what takes place in a reaction after the reactions start to react, all the way up to the time at which they convert to products. That's the kinetic region. We need to observe this reaction speed. How can we observe reaction speed? Well, we have to observe reaction speed in terms of change in concentration of reactants as the reaction proceeds, or change in concentration of products as products begin to be produced. Because these are the measurables. That's what you have. Reactants, originally. So let's operate on observing their changes in concentration, which will be a negative value, because their concentrations are going to get progressively smaller. So you've got to do a little arithmetic in order to not mess around with negative signs. We'll talk about more about that later. Or change in product concentration, which is positive, because the product concentrations or amounts are getting larger as the reaction proceeds. Okay? But the other part of the puzzle is, what are these reactants doing from a molecular structure and geometry standpoint, from an interaction standpoint, in this kinetic region? What are they doing as they actually engage in structural rearrangement and valence electron rearrangement to convert to products? To me, that's the real fun part of this kinetic study. This is the mechanism part. Shorthand, abbreviational reference, MXN. This is the reaction path by which the reaction proceeds, and it's usually 2 or more steps. Now let's define this step. Each step in a mechanism, got too close to the board. It's called an elementary process. It's simply a fancy term for a reaction which occurs in a single step. And when you have the reaction equation for an elementary process, that reaction equation is showing you specifically what particles and how much of these particles are involved in that step and become the indicated product or product in that step. So I wrote an elementary process is really simply put a reaction occurring in a single step. And now we have a rule applied to these elementary processes. If we have a reaction which is known to proceed by 2 or more steps, involve 2 or more elementary processes, well, is this mechanism legitimate? Does it really fit with the kinetic behavior of this reaction? A test with which a proposed mechanism must meet in order for it to be plausible, in order for it to be valid, is that when you sum up the steps algebraically, sum up the elementary processes, you add them up. Just like, remember when we did this kind of stuff with Hess's law? Same idea. You add up the elementary processes algebraically, just like you did with Hess's law stuff. Because they must equal the net stoichiometric equation for the reaction that's being studied. If the sum of the elementary processes does not do this, that can't be the mechanism by which the reaction proceeds. All right? Now let's take a look at an example, and that's how I see it. Here's where the fun starts. Because this is very appealing to horse sense. A gas phase reaction. HCCl3 gas plus Cl2 gas becoming carbon tetrachloride gas and hydrogen chloride gas. For starters, when we look at this reaction equation, we can immediately focus on the question, what happens as this reaction proceeds? The equation for the reaction, let it talk to you. Does this reaction equation demand the recognition that as this molecule converts to this molecule, a carbon-hydrogen bond has to break? There's no carbon-hydrogen bonds in any of these products. Does this collection of products also show you there are no chlorine-chlorine bonds? I mean, you remember what this stuff looks like? You remember how to write the Lewis structure for this thing? Carbon tetrachloride. A model, never mind, forgot to bring them up, green ones. So the green ones are symbolizing chlorine atoms. So imagine for now this is a chlorine atom. So this is a carbon tetrachloride molecule. A perfectly tetrahedral molecule, okay? Well, now we're going to use this to simulate this reactant molecule, trichloromethane. Never mind its name, who cares? Just call it HCCl3. Now, unfortunately, the people that made this model cube didn't supply parts where some of the spherical atom representatives are larger than others. That's too bad. So, in your mind's eye, I want you to look at this as the hydrogen atom. And these are each these big chlorine atoms, okay? 3 big chlorine, okay? You can draw a picture on your paper. Do that for yourself. Okay? Now then, we recognize that this proceeds, a carbon-hydrogen bond has to break, a chlorine-chlorine bond has to break, and a carbon-chlorine bond has to make, and a hydrogen-chlorine bond has to make. Okay? So before, finally, so in thinking about a possible mechanism, what might occur involving this reactant and or this reactant to get the reaction started? Well, what might occur is that first the carbon-hydrogen bond breaks, or a chlorine-chlorine bond breaks. Is that reasonable? Or the chlorine molecule comes apart. What have we considered previously that will allow us to get a reasonable answer to this question? And we looked at bond energies, bond strengths. All right, so we're going to get out our table, which I have my memories right was included in chapter 9 and chapter 10. We have bond lengths and bond energies. And in this table, you'll find a carbon-hydrogen bond strength and a chlorine-chlorine molecule bond strength. Now, the carbon-hydrogen bond strengths are average bond strengths, but it'd be good enough for this consideration. I wrote the information down here. Let's see, carbon-hydrogen. Where are you, carbon-hydrogen? Someplace in my scribbles. Here it is. 414 kilojoules per mole versus 243 kilojoules per mole. So if it is true that this reaction starts, step 1 for this reaction is the breaking of a carbon-hydrogen bond homolytically or a chlorine-chlorine bond homolytically, which do you think is more likely? Well, a weaker bond, okay? So here we go. Now, at this point, what do we have in the reaction vessel? Well, we still got chlorine molecules which haven't fallen apart, and we got these molecules. We've got no products yet. Okay? So we got these, we got this, and now we got some of these. And now we wish to make a decision as to what might be a possible second step to get us forward forming these products. Well, we got this hot chlorine atom in here now. Here's our hot chlorine atom, okay? And remember what this thing looks like. Big chlorine atom, big chlorine atom, big chlorine atom, little hydrogen atom, and a carbon atom right in the middle. Well, this carbon atom in the middle there's carbon in the middle. There's our hydrogen atom in there. This carbon in the middle is surrounded tetrahedrally by a big chlorine atom, a big chlorine atom, a big chlorine atom, and a small hydrogen atom. And they're all in physical contact, these atoms, with each other. There's no sticks that indicate where the bonds are. We just use these in making models to show you where the bonds are. It's really, this is over here. This is over here, and et cetera, et cetera. So do you think it's entirely possible, or do you think it's likely, that this chlorine atom, which is produced by this first step, is going to bop into that carbon atom somehow that's in the middle, which is being surrounded by all these other atoms? Or do you think it's more likely, even though the hydrogen atom is small, that it can bop onto a hydrogen atom? Because that's on the periphery of this molecule. Now, if it bops into a hydrogen atom, it can make an HCl bond, can it? And that's part of a product, isn't it? Okay, so we're looking at two prospects for step 2. Prospect 1, Cl atom hits HCCl3 to make carbon tetrachloride molecule and a hydrogen atom. In other words, this thing went over here and managed to bop this carbon atom to form a carbon-chlorine bond while causing the carbon-hydrogen bond to break. Or this chlorine atom hit this hydrogen atom, likely because it's on the periphery of the molecule, as opposed to being the dead center of the molecule, to make this stuff. And this stuff. Might we do an energy consideration or apply an energy consideration to make a decision between these two steps? We've already made a steric consideration. This is sterically hindered. Because carbon is surrounded by peripheral atoms. You know, it's like if you're really mad at me and you want to punch me in the belly. Well, if I got a whole bunch of you standing around me like this, ha ha, you can't get me, because I'm being sterically hindered from your being able to punch me in the belly. What if I'm a hydrogen atom on the outside of this molecule, and that's my noggin, and instead of punching me in the belly, you want to hit me in the head with a hammer. Ah, you can do that! You bad person, you. Okay. So, we recognize from a steric standpoint, this interaction is more likely than this interaction. Now, could we apply any considerations of a thermodynamic nature to this? Bond energies. Because this makes a carbon-chlorine bond, doesn't it? And it breaks a hydrogen-carbon bond. Right? Well, we already got the hydrogen-carbon bond energy someplace. Where is it? Here it is, 414. So we want to take a look at carbon-chlorine. We'll get back to our table, and our table shows this is 339. Well, this is energy-wise not good. This is endothermic, isn't it not? Because to break the carbon-hydrogen bond, which is part of this step, it costs 414, but you only get a payback of 339. Well, let's take a look at this thing. In this case, we're making a hydrogen-chlorine bond and breaking a carbon-chlorine bond. I mean, we're breaking the carbon-hydrogen bond and making a hydrogen-chlorine bond. Okay? So what do we need here? We need a hydrogen-chlorine bond. That's 431. Ah. So, this involves breaking a carbon-hydrogen bond, right? Across 414. But we get a payoff of 431, making the hydrogen chlorine bond. So this one is exo. This is endo, and this is sterically hindered. So what's your better bet for step 2? This or this? This one. All right, so out goes this. And now, we're in a position to consider this reaction coming to conclusion. Because what do we got so far? After this step, and this step is out. Okay? We've got ourselves a hydrogen chloride molecule, which is a product of the reaction. And we've converted chlorine molecule to HCl, but there's still one of these left in there, isn't there? Only one chlorine atom was used in this step. All right? Well, if we just now pay attention to what's in the pot, we got the HCl molecule made. We got a chlorine atom in there that's ready to react. And we got something in there with which it is very likely to react, don't you think? Chlorine, pardon, not a chlorine molecule, but a chlorine atom. We got this in there now too, don't we? Okay, so 3. The remaining chlorine atom gets together with this carbon trichloride radical and makes the remaining molecule, product molecule. And if you add these up, you got this. Makes this mechanism plausible. Okay? Now some more language. For this reaction, Cl dot and dot CCl3 are reaction intermediates. And what I'm telling you is all in the notes. What's a reaction intermediate? Now, if we pay attention to our mechanism, we will see that a reaction intermediate is a stuff that's part of the reaction that's produced during the reaction and consumed before the reaction finishes. Right? It's not part of the original reactants, it's not part of the final products. What do you think about the reactivity of reaction intermediates? It's not part of the original reactants, not part of the final products. Think they're pretty reactive? Well, yeah, I mean, nothing else. I mean, these are radicals. They got unpaired electrons ready to partner up with other particles with unpaired electrons to make covalent bonds. Sure. Now, the other part of this puzzle, or the other parts of this puzzle, which we've not yet considered, I'm going to lay foundation for this in brief right now, and you're going to carry on with this tomorrow, is, do you think that when the chlorine atom, produced by step 1, hits this thing, okay? Because we recognize this to be step 2. Do you think the chlorine atom, when it hits this thing, guarantees this reaction? If you have a nice new, I don't know, nice new fancy car, whatever, Cadillac, okay, you got a Cadillac. You motor over here. You park the Cadillac in the, where we were allowed to park. And a bird flies over and molts a feather. Feather comes down and lands on the hood of your new Cadillac. Is that a collision? The feather of the bird hit your car. Yeah, it's a collision. But it didn't cause a dent. Okay. Now, unbeknownst to you, Where you've parked is next to the Gator practice field. And there's Gator Strongman practicing with the shot put. Doesn't know how strong he is. There goes a 16-pound shot. Pow! On top of your Cadillac hood. Is that a collision also? Does that cause a dent? Yeah! But there's a big difference between these collisions, right? One has a heck of a lot more energy associated with it. Okay? So another part of this puzzle we haven't considered is activation energy. How much energy must be associated with collision in order to get a reaction to in fact proceed? And the other part of the puzzle is, how must particles be oriented in space to interact with each other? Well, let's go back to this chlorine atom. Is it likely this chlorine atom will attack this by hitting the chlorine atom? Very likely. The chlorine atoms are on the outside. They're a heck of a lot bigger than the hydrogen atom, and there's 3 of them. Will that get us any place in the products? No. But it's very likely. Is it likely the chlorine atom will hit this other chlorine atom and go back to become CO2? Sure. That's not getting us any place either. Okay? So what we recognize is that in order for this to happen, this chlorine atom has got to hit this hydrogen atom. The only way this step can go. And it's not going to hit this hydrogen atom with a sufficient quantity of energy. So in brief, let's imagine that we're going to study a simpler reaction from a kinetic standpoint. And I hope at a glance that at least to some of you this reaction looks familiar. Because I discussed it in detail in the discussion section for assignment 8 that you did in laboratory regarding kinetics. Now, hydrogen molecule. Okay? Hydrogen molecule. Fair enough? I atom's a lot bigger than H atom. If I am going to believe that the hydrogen molecule, iodine molecule reaction proceeds in one step, which means in one step I'm breaking a hydrogen-hydrogen bond, breaking an iodine-iodine bond, and making 2 HI molecules, which means I'm forming 2 HI bonds, right? If that's going to happen in one step. And here's my I2 molecule in the gas phase floating around, and here's my H2 molecule in the gas phase floating around, and they're contained in the same reaction vessel. Is it likely that these particles will hit like this? Of course. Will this allow the reaction to go in one step? Because if they hit like this, how many HI molecules can I make? 1. How about if they hit like this? 1. How about if they hit like this? But how about if they hit like this? Ha-ha! So now we looked at another part of this puzzle called collision orientation. And this geometry of this collision orientation also has a name. It's called activated complex. An activated complex, you'll go into further tomorrow in discussion class. It's part of the notes. It's part of a reaction, which practically speaking has a 0 lifetime, because once you make this activated complex, given that its lifetime is essentially 0, one of 2 things is likely to happen. The activated complex will come back apart, and you'll still have an I2 molecule and an H2 molecule. Or instead, I broke the HH bond and made an HI bond, and I made another HI bond and made my 2 HI molecules. I'm going to go one way or the other when I get to this very reactive thing called an activated complex. You had a comment?
On the previous reaction that you had said about the CCl3, one of the other means that you know that that's the correct mechanism is a side product from that reaction where you have C2CL6 also formed.
What Ben is saying, if I heard it correctly,
Yeah.
is that these could react with each other. Okay? and make this stuff. Right? Sure, it's all possible. It's entirely possible. And people who study this, or pardon me, people who study this reaction, will look for that and see if that is a side product for the reaction. It's entirely possible. Okay? But if this hits another like it, with the carbon atoms hitting each other, bingo. And this is the kind of fun stuff you have when you think about reaction mechanisms, because it will rest on fundamental thermodynamic considerations we paid attention to previously, like bond energies, and more importantly, molecular structure.